Hi. According to Bohr atomic model, in an isolated atom, the energy of any of its electrons is decided by the orbit in which it revolves. But when the atoms come together to form a solid, they are close to each other. So, the outer orbits of electrons from neighboring atoms would come very close or could even overlap. This would make the nature of electron motion in a solid very different from that in an isolated atom. Inside the crystal, each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy level. These different energy levels with continuous energy variation form what are called energy bands. The energy band, which includes the energy levels of the valence electron, is called the valence band. The energy band above the valence band is called the conduction band. With no external energy, all the valence electron will reside in the valence band. If the lowest level in the conduction band happens to be lower than the highest level of the valence band, the electrons from the valence band can easily move into the conduction band. Normally, the conduction band is empty, but when it overlaps on the valence band, electrons can move freely into it. This is the case with metallic conductors. If there is some gap between conduction band and the valence band, electron in the valence band all remain bound and no free electrons are available in the conduction band. This makes the material an insulator. But some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move into the conduction band. At the same time, they will create a vacant energy level in the valence band where other valence electrons can move. Thus, the process creates the possibility of conduction due to electrons in the conduction band as well as due to vacancies in the valence band. Let us consider what happens in the case of silicon or germanium crystal containing n atoms. For silicon, the outermost orbit is the third orbit, n is equal to 3, while for germanium it is fourth orbit, n is equal to 4. The number of electrons in the outermost orbit is 4. Hence, the total number of outer electrons in the crystal is 4n. The maximum possible number of electrons in the outer orbit is 8. So, for the 4n valence electrons, there are 8n available energy states. These 8n discrete energy levels can either form a continuous band or they may be grouped in different bands depending upon the distance between the atom in the crystal. At the distance between the atoms in the crystal lattice of silicon and germanium, the energy band of these 8 states is split apart into two which are separated by an energy gap. The lower band, which is completely occupied by the foreign valence electron at a temperature of absolute zero, is the valence band. The other band consisting of foreign energy states called the conduction band is completely empty at absolute zero.